Okay, good evening, students. Welcome you all to the live session 10 of NPTEL course. So, we have already waited 5 to 6 minutes for other students to join. So, yeah, let's start this session now. So, like previous sessions, this session is also planned according to the uh, planning of previous session as we have discussed. Uh, So this session is basically live session 10, uh, live session 10 of NPTEL course Physics of Renewable Energy Systems. And this course is taught by Professor Amrish Chandra. He is from Department of Physics, IIT Kharagpur. And the live session is taken by Rohit, which is me. I am PMS scholar at IIT Bombay. So, what I have planned for today is that we will discuss the revision of the previous session, whether in that we will discuss the concepts which we have discussed in a previous live session. Also, we'll take up the assignments, old assignments question, and try to solve them, grab the concepts behind these assignment questions. So, and then we will move to the discussion part where we will take an discussion uh, your major questions which are related to this live session, or if you have any minor doubts you can ask in middle also, so we will take up those doubts and discuss it in the class itself. So if there are any major doubts, I would suggest that you ask it in the discussion forum so that everybody could benefit from it, from the answers, and a wide discussion can happen. So I think it's already 7:10, so uh, we should start the session. Okay. So we see that in previous session we discussed about different concepts of fuel cell, different types of fuel cell, how they operate. Also, we talked about the term hydrogen. So we had a question that how much is the calorific value of hydrogen, and we talked about the term hydrogen economy. So, what is hydrogen economy? Hydrogen economy originates from the term hydrogen. So it is a concept in which hydrogen could be utilized for a long range of application, like for fuel, for replacing gasolines, for cooking, for everything. So hydrogen is a very high calorific value fuel. Like it has a calorific value of uh, 150, around 150 megajoule per kg, which is almost three times the calorific value of gasoline which we use for fuel today. That's a quite high amount. So when we talk of hydrogen, we generally envisage a fuel. But the main problem with hydrogen is that the hydrogen is in gaseous form in normal temperature and pressure. So you know the term normal temperature and pressure. It's 25 degrees Celsius and 1 atm pressure, 1 bar pressure. So at normal temperature and pressure, the hydrogen is in gaseous form. But a major problem is that ki hydrogen is having so much of calorific value, such a high calorific value, but still it can't be utilized. So why it can't be utilized? This is the main question. Main question: the hydrogen, instead of having a very high calorific value, we don't see hydrogen being utilized in industry and utilized in transportation at a much higher scale or commercial scale. So the main reason behind it is कि hydrogen, if anything is to be utilized on commercial scale, it has to be available. So availability is a criteria. Another thing is that it has to be available at cheap price, at economical price. I don't say the word cheap price. I would rather prefer economical price. Compared to gasoline, we have a comparable price of hydrogen. That's when we are going to replace gasoline with hydrogen. And also the properties should match the properties of engines or the devices or any other things which on which we are going to use hydrogen as a fuel. So mainly when we see hydrogen, there are actually three things which I want to discuss here. I think we have discussed this in last class also. If anybody could remember it, it was actually the first thing is, if anything is to be used as a fuel, the first thing is production. So how do we produce hydrogen? Anyone? Yeah, sure. So we produce hydrogen by electrolysis. And what is electrolysis? Then the question arises, what is electrolysis? See, electrolysis is basically breaking up of the bonds of water into hydrogen and oxygen. That's a quite difficult and I would say energy consuming phenomena. It takes a lot of energy to break the bonds between hydrogen and oxygen. So quite difficult to get hydrogen at by breaking the bonds of hydrogen and oxygen. So one thing is it's quite difficult to produce hydrogen. Second thing is when you produce hydrogen by any means, like you have the hydrogen. So there are many other processes also hydrogen. Like one of them is gasification. So gasification reactions also produces hydrogen, like water gas shift reaction and some other reactions also. So there are methods. So let's assume that we have a host of production methods and we produce a lot of hydrogen. But how do we transport it? That's another thing. You have gasoline, so you have a proper infrastructure framework for transporting gasoline from or coal from one place to another. Like kind of coal it transports through conveyor belts or in trains, trucks. Gasolines are in tankers stored in compartment tanks. So that's how transportation occurs. But how do you transport hydrogen? It's in gaseous form, first thing. So there are always chances of leak, if any, and they are highly flammable. So if there is any slight fire, so there is always a chance that the whole thing gets burnt up because of high calorific value. It will react very fast and you will see a lot of damage to the neighborhood also, adjacent neighborhood. So it's quite risky, poses hazard also. The second thing is that let's assume you don't transport it in the form of gas. So how another two thing is you transport it in the form of liquid or you transport it in the form of solids. So in form of liquid, if you convert hydrogen to liquid, so you will need a lot of nitrogen based HVAC systems to convert or cooling systems to convert it into liquid hydrogen. Then another problem with liquid hydrogen is that there is a sloshing phenomena in liquids, especially when There can be sloshing when you're transporting the hydrogen through in liquid form. There can be, first thing is that you need to spend a huge amount of energy to maintain it in liquid form. Another thing is that the sloshing phenomena, it can be dangerous also. So if there are, since hydrogen is highly flammable, very high calorific value, so if there are any mishap, it can lead to a severe disaster. The third thing is that you transport it in the form of solid. So when I'm talking about gaseous transportation, liquid transportation, solid transportation, so it's basically that I'm talking about storage also. These are the various forms in which hydrogen can be stored: the gaseous form, the liquid form, and the one which we are talking about, the solid form. So how we are going to store it in solid form is the main question. So this phenomena is actually tackled by metal hydrides. So what happens that metal reacts with hydrogen and form metal hydrides. These metal hydrides can be stored, can be transported to any place, and then after requirement of hydrogen is raised, these metal hydrides can undergo reaction or through catalytic process. These reactions can be fast tracked to produce hydrogen. Okay, so that's how the hydrogen is actually stored or transported. And we talked about the production also. There are several methods of production. The one was basically electrolysis, and the second was through gasification, or you can do any other catalytic reactions that can produce hydrogen. Okay. So that's the whole thing about hydrogen economy. Second thing is that what are the greenhouse gases and how do we measure them? You know the term greenhouse. Greenhouse is a term that is originated from the colder countries in which they build a greenhouse just to preserve the plants, to provide them warmth or hotness so that they can get accustomed to a warmer temperature and can grow fast. In colder regions, there is no sun, and due to the cold outside or lower temperature, these plants can die. That's why they build structures, and these structures are basically where greenhouses. They're called greenhouses, mostly due to the color. Maybe the color of the house could be green. So it's not a house; it was a structure. Okay, and in these structures, the plants are actually placed, and these are totally packed structures. So it maintains a optimum temperature for the growth. And actually, in recent years, recent decades, like after 1980s, 90s, when we start thinking about climate, so we got to notice that there are certain gases which are actually doing the same thing with Earth. So there in greenhouses, it was doing with plants. Here it is doing with Earth itself, the atmosphere. So what it is doing, it is trapping the heat of the sun. The heat is coming through sun ray, and there are certain gases which are actually more potent to trap the heat. Like if I name these greenhouse gases, so how do these greenhouse gases are actually measured? These are measured with reference to a specific gas which is CO2. So CO2 is given a reference one, and all other gases are basically measured in times, how many times it is more potent to have a greenhouse effect, sorry. When we see that, and this whole term is called, since it is an environmental impact, so there is impact category, and it is called global warming potential of the gas. What is global G warming W and potential peak GW peak, global warming potential. So for measuring the global warming, that's how it is measured, the greenhouse gases. Okay, you got the answer. And the major thing is that when we measure a greenhouse gas, the major thing is that it has to be measured with some reference. So we take CO2 as a reference, I allot it a value of 1. So it's according to CO2, the methane CH4 has a value of 21. So it is actually 21 times more potent global warming potential than CO2. Similarly, some refrigerants have like R32 has a global warming potential of 600 or 700 something. R R407C410 has around 1600 to 2000 global warming potential. So see these quantities, they are 600 times. R32, the best refrigerant in the market, which has a very low global warming potential, is itself 600 times more potent for a greenhouse gas. That's why it is very important to tackle these systems and to know this system very carefully. How know this system of measurements very carefully actually. The third thing we discussed that day was microbial fuel cell, and we know that fuel cell is just like a battery in which there is a cathode, there is an anode, and there are some redox reaction at the cathode and anode, and the electron is produced, which is taken to the outer circuit and passes through the load to produce electric current. Okay, so what happens in microbial fuel cell? And so microbial fuel cell is also a same thing. It's an electrochemical device. And what happens that at anode anaerobic digestion reaction occurs. And the bacteria when acts on the carbonaceous content. And what is carbonaceous content? So you can always ask the questions. What is carbonaceous content? You don't know. So carbonaceous contents are those contents of sewage, sewer, or dust particles since, and if it has some carbon containing elements, so it's called carbonaceous content. Maximum amount of that element should be carbon. Okay, so these carbonaceous contents undergo anaerobic digestion, and rest other people go through rest other thing. A fuel cell goes through the simple cathode anode reactions, and microbial fuel cell has anaerobic digestion reaction at anode. Okay. So what happens when bacteria actually works on these carbonaceous content, organic content? A reaction takes place and it produces an electron. That electron is taken out and flown in as a form of current to the cathode, and it completes the circuit. So when we see the definition of a microbial fuel cell, it is basically a bioelectrochemical device. Why bio? Because bacteria acting on anaerobic digestion, and that can generate electricity. The use of electrons obtained from the anaerobic oxidation of substrates. So when it's a substrates, it's carbonaceous content, okay, carbon matter. And we move to the slides of today. So till the revision, is there any questions, students? You want to ask any questions? The questions are always welcome. It is encouraged for you people to ask questions so that we also know that we are going in the right direction. You guys are learning actually, or if there are anything that can be that needs to be discussed, so it can be discussed very easily here. Okay, you are also encouraged to ask them in discussion forums so you can have a wide understanding to discussion. Okay, now the question number one is critical radius of a particle is. The options are proportional to the surface tension. Option B is inversely proportional to the surface tension. Option C is proportional to free energy. Option D is none of the above. So critical radius is a term that generally uh, utilized in case of surface tension evaluations. So what happens in case of surface tension? The surface actually experiences a tension and it behaves as a stretched membrane. Okay, it's not like a normal surface. It starts behaving like a stretched membrane. Okay, so at that term, at that at that instance, there is a term critical radius associated with surface tension. So the more the surface tension, the more will be the critical radius. So it is proportional to the surface tension. Okay, so the correct answer here is answer A. So critical radius is directly proportional to the surface tension. It is not inversely proportional to the surface tension. It is directly proportional to the surface tension. Now another thing, nanolithography. So what is nanolithography? So you will have to first understand the term nano, litho, and graphy. Okay. So what is nano actually? Nano are special class of materials that has any one of the dimensions in 1 to 100 nanometer. Okay, so if anything which has one of the dimension in 1 to 100 nanometer, it is nanomaterial. And lithography is a technique of printing, like artistic writing lithography. Okay, just like a printing process, lithography is a printing process that uses a flat stone on which the image areas are worked using a greasy substance so that ink will adhere to them. Okay, so in case of nanolithography, it's basically a technique of production of nanomaterials. So there are various techniques of production of nanomaterials which are listed below as options, like biological synthesis methods, chemical synthesis methods, physical synthesis methods. So these are different methods for production of nanomaterials. And what happens in biological synthesis methods? So try to grasp the name itself. If you could understand the concept behind the questions, you will know the answers very easily. So, like what should happen in biological synthesis? It must be through biological biomatters or bioorganism like fungi, bacteria, or something. In the chemical synthesis method, you utilize chemicals like Solgel method is a chemical synthesis methods. Similarly, other methods like chemical vapor deposition. Third is physical synthesis methods in which physical strength or physical properties are used for producing nanomaterials like ball milling method, buttering, etc. So these are the different methods for production of nanomaterials which are quite commonly used. There are several classifications in these methods also, but be sure that they are all very good utilized methods for production of nanomaterials. And if you see the nanolithography, it's basically lithography. Lithography is engraving something on the it's like printing something, so that's how it is made. So nanolithography is basically a physical synthesis method. So the correct answer is answer C. Now the question number 3. Chemical activity of a catalyst can be improved by increasing the surface area, decreasing the particle size, and introducing porous structures. Basically, when you have a specific more surface area, like more specific surface area, so what happens? There are more nucleation sites, more reaction sites available for the reaction, and this actually boosts the chemical activity of a catalyst. So catalyst has to act the more surface area the catalyst gets, the more better it will be for the reaction, that it will always try to grasp the more surface area. Okay. Second thing is decreasing the particle size. So it also actually improves. When we decrease the particle size, the surface area to volume ratio actually increases. That has a very good impact on the chemical activity of the catalyst. Third is introducing porous structures. So increasing surface area is also similar to the increasing porous structures. It behaves on the same path. Uh, okay, so the correct answer is answer A, increasing the specific surface area. It also decreases the surface particle size, can improve the chemical activity of the catalyst, and reducing porous structures can also help. Now the fourth question. The fourth question is generally the micropores are associated with pore width less than 2 nm with cylindrical shaped pores, pore width 2 to 50 nm with slit shaped pores, pore width greater than 20 nm with cylindrical phase pores, and pore width greater than 50 nm with slit shaped pores. So basically, it's asking about micropores. Micropores, it's in dimension. And what is micro dimension? It's 10 to the power minus 6 meter. Okay. So generally, it's a conceptual question which can be answered by seeing the slides. So basically, it's a micropore. So options C and D can be eliminated at the one go, like it is talking about the greater than 20 and 50, and there can be two options from less than 2 nm and 2 to 50 nm. So micropores are basically 1 upon 10 to the power minus 6 meters. So that's why the option A suits best. The pore with less than 2 nm with cylindrical shaped pores. Okay. So there can be questions on similar pattern in the exam which you have to uh, grasp from the concepts from the slides itself. The fifth question is graphene. Graphene has a dash dimensional lattice. So there, I think we have talked about the dimensionalities in the first live session itself. Sir has actually started this session with the graphene concern, sorry, dimensional lattices itself. So how many types of lattices were there? BCC, body centered cubic, trans connection, body centered cubic, sorry, not France, face centered cubic. So and primitive cell, okay, unit cell, unitary cell or something. So these are the dimensional lattices, the arrangement of atoms in the at different positions. So when we talk about graphene, graphene is very much widely used material. It has a host of applications, and you don't even know that where it cannot be applied. It can be applied at a lot of places. Graphenes are actually used in bulletproof jackets, also in batteries, for cooling purpose, for manufacturing of carbon nanotubes, and a lot of things. And basically, it's a conceptual question. So it basically asks graphene as a how many dimensional lattice? It's basically graphene has a two-dimensional lattice. Why two-dimensional? Why not three-dimensional? Actually, what happens that graphene layers are actually two-dimensional in length and breadth, and it doesn't have height. It's basically a two-dimensional lattice. So the correct answer is graphene has a two-dimensional lattice. Now the question number 6. Which of the following scientists is considered as father of nanotechnology? I remember this also we have discussed earlier in most of the lectures. Uh, I think in lecture 6 or 5 we have discussed this. So what happens actually is that there are four options: Feynman, Newton, Maxwell, Pauli. So what happens is we don't think we know the answer, like who is the father of nanotechnology, or who is the father of India, or who is the father or mother of these things. It's basically it's an clear understanding to get to know these uh, personalities or scientists in their era, which have a very great contribution towards the progress of science in modern era. So question arises here is why Feynman is called father of nanotechnology. So actually he gave a very good speech at one of the universities in which he said that there is a plenty of room at the bottom. A very impactful line, and later he worked also at different quantum of projects, and he later worked he didn't have much contribution in the nanotech field, but his actually contribution in popularizing this field through this sentence, this lecture is actually a very good lecture in which he said there is a plenty of room at the bottom. So what happens is that when you have an atom, so when you break it in pieces, you will get a lot spaces because electrons are only utilizing a very small space. Similarly, the protons and neutrons. So in that context, it's a basically an atom is empty itself, and that's what the nanotechnology is based off. If we decrease the size, the surface area to volume ratio actually increase, and that has a lot of impact. Like if in a reaction you increase the surface area, so you can see that catalysts are working very efficiently now. Okay, so these are the things which actually promoted the field of nanotechnology. Now it has a severe host of applications in houses, in factories, industry, commercial products, and a lot of things. Okay, so for this question, the correct answer is the scientist who is considered father of nanotechnology is Feynman. Okay, so let me check if anyone wants to join. Anyone? Okay, now moving to the next. We have total of 11 questions. The question is what are the nanomaterials? So This question is actually taken from slides itself, and I basically put this question so that you know actually what are the nanomaterials. There is a lot of confusion about which material can be called as nanomaterial, which material cannot be called a nanomaterial. So it's it is not just that key you have produced a nanomaterial without any dimension, or it has one of the dimension or two of the dimensions uh, more than 1 meter, and the another dimension, the third dimension is in nanometers. So can it be called a nanometer? So, yeah, of course, as per definition given, any material which has any one of the dimension in the range of 1 to 100 nanometer is nanomaterial. Okay. So if we go by the definition of nanomaterial, it's a special class of material which has any one of the dimension in the range of 1 to 100 nanometer. This you have to remember because it's confusing. People ask that we don't have one dimension in nanometer and all the two dimensions are in nanometer. Can it be still be covered as nanometers? No. Probably yes also. You probably yes because it has one of the uh, sizes in nanomaterial. Okay, so the option below a special class of material which has all the dimensions in the range of 1 to 100 nanometers are not nanomaterials. If any, not only all the dimensions, it is a nanomaterial, but the correct definition is that which have any one of the dimensions in the range of 1 to 100 nanometer. So the question number 8 is basically nanomaterials have large, small, small, and normal materials very small. So this I have tried to prove mathematically also, so you guys could know. Uh, like, so basically, what could be the answer? There is large, small, same, and normal material very small. Okay. So basically, as the size is reduced, the surface to volume ratio is actually increasing. So nanomaterials have large surface area volume ratio. Okay. So I also try to prove it mathematically so that you guys could understand the concept behind it. It's not just that we have said nanometers have large surface area to volume. Can be proved also. So how? So assume that a material have a radius r and it is sphere. Okay. So what is its ratio of surface area to volume? So surface area is of a sphere is 4 pi r square. The volume of a sphere is 4 by 3 pi r cube. And what is the ratio? We divide the surface area by volume. The correct ratio is 3 by r. So what do you see here? The surface area to volume ratio actually increases when we decrease the size of the material. When the size of the material decreases, the surface area actually increases, and vice versa. Because they are inversely proportional, radius and surface area to volume ratio. Now coming to the question 9. Select the options which describes the properties of nanomaterials compared to normal size materials. So when I say a normal size material, it's basically regular material that is found. They, they have said to compare the properties of. So when a normal material like you say iron, it is converted to nanomaterials, it actually performs very very elastically, not elastically or there can be a lot of change in its characteristics. So the first option is enhanced surface area to volume ratio is actually read in the last slide. It also actually adds up to the low density because all the voids have been cleared and in powder form. The third is low mass requirement also. This is also correct. Fourth is change in conductivity. So this can also happen. E is all of the above. So the correct answer is all of the above. Answer A is also correct. B is also correct. C is also correct. D is also correct. E is also correct according to Lord. So E is basically all of the above is the correct answer here. The enhanced surface area to volume ratio, low density, low mass required, change in conductivity. So correct answer is answer E. Now the question number 10. Which of the following synthesis techniques are correctly matched? So when we talk of synthesis techniques, there can be three categories in which these synthesis techniques can be divided. One is biological synthesis method, second one is chemical synthesis methods, third one is internal physical synthesis methods. So in biological synthesis methods, we got to know that they use organism like fungi, bacteria, or something for producing the nanomaterials. The solid method is basically a liquid solution and solid dispersed medium. So it's basically a chemical method, and it's a very good chemical method for production of nanomaterials because one of the people which I have seen is working on this soldier method. So it's a quite interesting work he's doing on soldier method. This is also one of the main reason for classifying it is in chemical synthesis method because it involves chemical and chemical reaction. Laser ablation is physical synthesis method, sputtering is physical synthesis method, hydrothermal is chemical synthesis method, and it is bottom to up approach. Okay. So hydrothermal processes are basically processes that occurs in hydrothermal region like high pressure, uh, high temperature. Okay. For this, I think all of these are correct. So correct answer is answer F. So we don't find anyone who is not correct, which is not correct. Now the question 11. It's the last question of today's session. And if there are any queries from your side, you are always encouraged to ask them in class. If there are any other queries, you can always write to me or put it in discussion forum. So question 11 is statement 1. During a chemical reaction, a catalyst may undergo a physical change, but never a chemical change. So this is actually correct because in catalyst doesn't undergo a chemical reaction. Okay, it's it cannot change, alter it. Okay, so it can undergo physical change, but catalyst cannot undergo chemical change. So the statement 1 is correct. We go by statement 2 in reversible reaction. Catalyst catalyzes both forward and backward, that doesn't alter the equilibrium. So this is also correct. So catalyst, what does catalyst do? It augments the heating rate of the reaction, but then the heating rate of above sheet is heating. Uh, it's not a heating rate. Catalyst actually reaction rate. It increases the reaction rate. So in the case of forward reaction, it catalyzes it. So similarly, it catalyzes the backward reaction also. So when you catalyze the forward and backward at the same time, what happens that equilibrium position remains fixed. It's in the place, so it doesn't alter any equilibrium position. So statement 2 is also correct. So the correct answer is statement 1 and statement 2 both. Okay. So with these discussions, we I'm trying to end the current scenario of live session. And if there are any queries, you are always welcome to ask me. You can always write an email to me on this email ID. Also, I'm adding a link to the discussion on the uh, NPTEL forum. You can access it in problem solving session reminder. Okay. So if there are any queries, you are free to ask in today's class, or you can always write it to me also. So yeah, thank you guys for attending the today's session. It was a very nice and informative session. So I would like that you guys start reading this session and starts writing, also forming the uh, going through the slides of the professor, and he has quite beautifully explained all these concepts which you can learn. Okay. So we talked about a lot of things. We talked about the revision of the previous session, hydrogen economy here, which is an important part. Greenhouse gases, how do we measure them? Microbial fuses. Then we took up the questions from previous old run of assignments, and then we end the today's session. Okay, so if there are any queries, you are always free to ask. So I'll be here till 8 p.m. And if there are any queries, you can also write an email to me or ask it in discussion forum. Okay, thank you guys. So we'll meet at the next live session on next Saturday, 7 to 8 p.m.